Hilbert-Mumford theorem says that we should be able to get to this closed orbit by taking a limit along a co-character. And that's precisely what we saw yesterday. So define lambda of A is A0, 0, A inverse. And then indeed we find that the limit as A goes to 0, lambda A of x1. Okay. So the Hilbert-Mumford theorem tells you what happens if the orbit is not closed. What happens, on the other hand, if you take a limit, but the result is still in the orbit that you started with? And this is where we're going to prove this result that I mentioned a moment ago, that if the limit is still in the G orbit, that it's actually in the RUP lambda orbit. We're actually going to prove something. I haven't really proved anything in these lectures so far. There are going to be some proofs today, and this is the first one. There'll be some details missing, especially some kind of little bits and pieces of algebraic geometry that we're just going to have to take for granted. So we'll start with this lemma. Maybe the lemma looks kind of complicated. It's a technical looking lemma. Maybe you can't even remember what all the notation means. So maybe I'll illustrate this lemma by means of an example. So basically what this lemma is saying is that if you have an x, you have a v. My notation's not very good here. I shouldn't really call this x, I should have called this g probably, because this is an element of the group, not an element of the variety that we're looking at. Not a very good choice of notation. Okay. So here we have a G module V. We have a maximal torus T of our group G. We have a co-character lambda whose image lies in T, and phi is the set of weights for the torus on V. Okay, so you break your V up into simultaneous eigenspaces for the torus. That's the way to remember it. And what this result is saying is, or one consequence of this result, is that if you have some little v, such the limit with lambda exists, and we have some, let's call it g instead of x, then the limit of, we take the limit of g dot v now, it still exists. So the lemma is saying that when you hit v with g, you're going to change it in general. You can think of it as adding a piece on to the v that you had. And what the lemma is saying is that the new pieces that you're adding on are not spoiling the fact that the limit exists, because the weights associated to those pieces, any vector you can write as a sum of weight vectors, the weights that are associated with these pieces, their pairing with lambda is non-negative. So you're not spoiling the fact that the limit exists. Remember, we had this criterion yesterday for you have a point you have a point in v and you take the limit and you want to know whether it exists or not. You break your v into all of these weight pieces and you look at the pairing of lambda with each of the weights that you see. So maybe I can make this more concrete. Let g equal gl2 acting on k squared. Just in the usual way, matrix multiplication of vectors. And my convention is I have a square matrix and it's acting on the left on column vectors. Yeah? what's P lambda? If you remember the characterization of parabolic subgroups of GLN that we talked about yesterday, we see this is just the upper triangular matrices. What are the weight spaces? T. It's going to be pi, which is the space span, the subspace spanned by the first standard basis vector, and let's call the other guy the everything's quite prime for reasons that we'll come here. Okay, so all I'm saying is that the diagonal matrices here, then you have your obvious eigenspaces, which are the vectors star 0 and 0 star. Okay? And what are the weights? Explicitly, chi prime of this is B, chi of this is C. And then you check that lambda with chi prime is going to be 1, and lambda with chi is going to be 0. So where does the 0 come from? That's because you have the power a to the 0 down here. And where does the 1 come from? That's because you have the power a to the 1 up here. So what's the lemma staying in this case? So let V equal E2 in chi, and take something in the unipotent radical of this parabolic. And now let's look at U dot V. So what's that going to be? That's just going to be 1, 1, which is E1 plus E2. Okay? So here's the piece that we already had, here's the V that we already had, and this is associated to weight chi and lambda with chi 0. What's the new piece that we've added on? This is associated to weight chi prime, and the lemma says that the pairing of lambda with this new weight chi prime has to be positive because this u was in the unipotent radical up here. Okay, so this fairly simple example is illustrating what's going on in the lemma. You're going to prove a special case of this in the exercises. But in general, this just follows from the structure theory of reductive groups and a little bit of representation theory. This is a technical result that we need. And now we have the theorem, theorem 3.12. Take a G variety in the point, take a co-character, and expose the limit, suppose the limit exists and is still in the same orbit, then actually the limit is an RUP lambda conjugate of the point we started with. Okay? Now, the proof of this, first step is we may as well assume that we're working inside a G module, because we know that we can always put a G variety equivariantly inside a G module. That's the first step. Now, the second step, this is kind of a bit complicated, but I think if I draw a picture, it will help. So here's X. Here's X prime over here. And let's draw a picture of inside X. And now, travelling along a one-parameter subgroup, we can think of as giving us some kind of one-dimensional path through here. So here's a typical point along the path, lambda a dot x for some a. And now this argument up here is talking about something called the big cell. Don't worry too much about what that is, but the point is that this set here, p lambda, times the unipotent radical of p of minus lambda is big inside G. It contains an open, dense neighbourhood of the identity. Okay. This is just the set theoretic product, the set of all elements, something from here times something from here. And the consequence of this is that if you take x prime and hit it with elements in here, because this is big and it's got a nice open neighbourhood of the identity in it, we don't have a different colour, do we? There was a green pen that was lying around the other day, I seem to remember. Thanks very much. So this green thing here, this will be p lambda ru p lambda dot x prime. Okay? So when I say
probably p minus lambda.
Oh yeah, p minus lambda, yeah, thank you. Not just probably, definitely. Thank you. And so if I have some subset of G, then by, perhaps this is just obvious, when I write this, even if this is not a subgroup, I just mean hit this with all of the points in, maybe A is not a good letter. Okay, so we now have this big open neighbourhood of x prime inside the orbit, but taking the limit passes us along this path and gets us to x prime. So x prime is an enclosure of that's saying that if we go far enough along this path, eventually we're going to get inside this green stuff. Yeah? So this tells us lambda a dot x is in p lambda ru p minus lambda x prime somewhere. Okay, so this gives us lambda a dot x equals, what have I got here? gu dot x prime, where g is in p lambda and u is in ru p minus lambda. So now I just want to take the g over to this side and combine it with the lambda a. This is in p lambda. The image of lambda of a is also in p lambda. Lambda commutes, the image of lambda commutes with lambda a, so lambda a in fact is in L lambda. Yep. So apply G inverse to both sides. And we get G inverse lambda a dot x with u dot x prime. And I just want to call this H. Now we're going to take the limit of both sides. left-hand side exists, that's because both of these limits exist, and the limit of the product is the product of the limits. I'll say it really quickly and I hope you believe me. So the limit on the left-hand side exists. And actually, so there's a bit of calculation here which I'm just going to ignore because I decided to set you as an exercise the fact that this limit exists as equal to this. This is actually not so hard, and there's a couple of hints. And as I said yesterday, it's essentially the same proof that you might use in an analysis course to show that the limit of the product is equal to the product of limits. If you know about the categorical, the universal mapping property that the products of topological spaces have. And even if you don't, I'm going to tell you what it is in the exercise. So the limit as a goes to 0 of lambda a dot h dot x, because the limits of each of the pieces separately exist. So lambda a dot h, we're thinking of the group acting by conjugation, so that really means lambda a h, lambda a inverse. And this, so remember our characterization of parabolic subgroups yesterday in terms of co-characters. This is C lambda of H in terms of the notation yesterday. So H is in P lambda, and this just means the projection onto the Levy subgroup L lambda. And this limit is X. So the limit on the left exists, therefore the limit on the right must exist, because the stuff on the left, the thing on the left and the thing on the right that we're taking the limit of is equal. The difference is that on the right hand side, which we can't see anymore, so I'll go to the page. Actually, maybe I should just go up for a second. So here's the thing on the right hand side we're taking the limit of. This u is not an RUP lambda, it's an RUP minus lambda. So the limit of this thing would exist for minus lambda, but not for lambda. For lambda, the limit does not exist. Okay? But the limit of this overall thing exists, even though the limit of this piece doesn't exist. And we're going to see in a moment that the only way that that can happen, is that if this u is actually centralizing x prime. Okay? If we could get this u to disappear somehow, this h is in p lambda. And this is then telling us that x prime is p lambda conjugate to x. That's not quite what we want. We want x prime to be RU p lambda conjugate to x. But getting from p lambda conjugacy to RU p lambda conjugacy is not hard. And this is where we need that technical result that I spent a bit of time talking about before. The effect of all this stuff that I've written on the board is that if we look u dot x prime, this is equal to x prime plus pieces corresponding to weights chi prime with, so this is thinking of minus lambda now, with minus lambda chi prime is greater than 0 by this lemma. Applied to minus lambda. Okay? But this limit exists, remember? And if we see non-zero pieces here, then the limit with lambda can't exist, because then the pairing of lambda with these weights is going to be negative, and that will stop the limit from existing. Okay? So lambda with chi prime. Remember this pairing is bilinear, so this is minus lambda with chi prime. It's going to be less than 0. So the only way the limit can exist is if all of this stuff here vanishes. So the limit to exist, all of these pieces must vanish. These pieces, these guys here. Therefore, u dot x prime equals x prime. Therefore, x prime is equal to h dot x, which is in p lambda. So that's the hardest part of the proof. The rest of the proof is not so bad. Page. So now write h is equal to LV, L in L lambda, and V in RUP lambda. Usually I would call something in RUP lambda, I would call it U, but we already have a U, so I can't do that. So x prime is equal to h dot x, which is LV dot x. Both sides with L inverse, L inverse dot x prime is equal to V dot x. Take the limit. And now this time on both sides, I can use the limit of the product equals the product of the limits. Because both of these, the L inverse and the V lie in P lambda. One lies in L lambda and the other lies in RUP lambda. So I get C lambda of L inverse dot the limit of x prime is equal to C lambda of V dot the limit for x. But what's this? Lambda commutes with x prime. So this limit is just x prime. And C lambda of L inverse is just L inverse because L inverse is in L lambda. And L lambda is the things that commute with lambda. So I get L inverse dot x prime over here. And over here, C lambda of V, V is in the unipotent radical, so C lambda of V is 1. That was the characterization of the unipotent radical that we had. And this limit is x prime. That's up with the 1. So that's saying that this L inverse here is not actually doing anything. So x prime is equal to V dot x, which is in the unipotent radical. And that completes the proof. So this is why we needed this technical lemma. We'll see another reason later on why we wanted this technical lemma. Okay, open problem. All of this makes sense over an arbitrary field, not just an algebraically closed field, but an arbitrary field. And so the question, does theorem 3.12 work over an arbitrary field? So if limit exists and belongs to, let's careful. It's conjugate to the original thing by a k point. We hear k is some not necessarily algebraically closed field, and then everything that we see is defined over k. So this x here is a k point. This co-character lambda is k defined, and so on. Actually, this doesn't have to be a k point, it turns out. This can be any k bar point, where k bar is the algebraic closure, and that doesn't change. That's x prime belong to the RUP lambda k points. Don't know the answer to that one. My collaborators and I have been thinking about that for quite a while, but we get stuck. So a corollary there.
You could leave it as an exercise.
I could leave it as an exercise. I think that one would probably be 3 stars or maybe even 4 stars. Believe me, I've spent a lot of time thinking about this problem. When my son was little, he used to have someone, he found it very hard to go to sleep, and he liked to have one of his parents lying beside him in bed. You know, it's not so uncommon for small children. But the other thing was he would take a very, very long time to go to sleep. So I would be lying in bed beside him for an hour or an hour and a half and 2 hours waiting for him to go to sleep. Think about this problem. I wasn't able to solve. Okay, so a corollary, and maybe I won't actually write anything down for this. Maybe I should write something down. So you take an x, and you suppose the limit exists. The limit belongs to the orbit, if and only if. Well, what we've just proved is that x prime belongs to g dot x, if and only if x prime belongs to RUP lambda dot x, this smaller subgroup. Okay, and here's a useful criterion saying that x prime is equal to u dot x is equivalent to saying lambda fixes u dot x. So here u is in the uniform range. When I say lambda fixes u dot x, I mean the image of lambda under the action. Half of this we've proved already, because it's essentially just the theorem that we did. The part that we haven't proved is if lambda fixes u dot x, then, well, if you have a point that's fixed by lambda, then when you take the limit, nothing happens, yeah? And then the limit of the product is the product of the limits. Lambda of u is just 1 because u is in the unipotent radical. We get x. Yeah. So if lambda fixes u dot x, then it has to be the case that u dot x equals this x prime, and therefore this x prime is RUP lambda. Nothing too tricky going on there. Okay, now we move on to section 4. And we're going to see finally our geometric criterion that we keep on talking about. So we have this action by simultaneous conjugation that I talked about before. Here's the formula again. We call the orbits conjugacy classes. Sometimes people will call these simultaneous conjugacy classes. Simultaneous is a long word to write, so I'll just call them conjugacy classes. And we're interested in subgroups that are generated by these tuples. So take a tuple of elements of G, H1 up to Hm, and we'll use this vector notation often we'll use this vector notation to represent the tuple. we define this curly G of H to be the closure of the abstract group that's generated by these HIs. Okay, so this will be some closed subgroup of G. And we say that a subgroup is topologically finitely generated if you can obtain it in this way. Maybe you're tempted to ask me which subgroups are topologically finitely generated and which are not. Don't ask, because I'm going to talk about that in a minute. Okay, now this is this great idea of Richardson. It's very simple, like many great ideas, it's very simple. If you conjugate your tuple by something, then you conjugate the subgroup that it generates by the same thing. So the subgroup generated by G dot, the sort of tuple of H, is just the conjugate of the subgroup generated by the original tuple. So if you want to study conjugacy classes of subgroups, you can do this indirectly by studying conjugacy classes of tuples. Now, why would you want to do that? The reason is that if you're studying conjugacy classes of tuples, you're in the world of geometric invariant theory, because these are tuples in some G variety. And so you can apply tools from geometric invariant theory to prove things. You can apply geometric ideas. So this is what we're going to do. So here's the statement. Theorem, take some tuple, H, look at the subgroup capital H that generates. Capital H is G completely reducible if and only if the conjugacy class, this tuple, is closed. Okay, so G completely reducible subgroups correspond to closed conjugacy classes. So I should write down something about the proof of this. So suppose H is G completely reducible. So take a co-character lambda. Suppose that the limit exists. So suppose, okay, we want to show that the orbit of this tuple is closed. The Hilbert-Mumford theorem, or the corollary to the Hilbert-Mumford theorem that we wrote down, says it's enough to take limits of co-characters and show that this doesn't get you outside the orbit. Yeah? So let's do that. So here's a co-character, the limit exists. We want to show that it's in the same, orbit. Now, what does this mean if we spell this out in detail? And if this big limit exists, then the individual limits of all of the entries also exist. That will be part of the exercise that I was threatening to give you before, which involves proving what the limit of the product is the product of the limits. So the limit exists. Exists for each I. But if this limit exists, it's saying precisely that HI is in P lambda. And it follows from this that capital H is the subgroup generated by these things, or the closure of it, so therefore H is contained in P lambda. Now we can use our G-complete reducibility assumption. This tells us then that H has to be in some Levy subgroup of P lambda. Actually, because we've got this lambda lying around, really what we want to do is not work with any old Levy subgroup, but work with the Levy subgroup L lambda, which is the centralizer of the image of lambda. That's the natural Levy subgroup to work with in this context. Okay, as H is GCR. Perhaps I'll just finish this direction of the proof, and then we'll have our 5-minute break and do the other half afterwards. As H is GCR, some conjugate lies in L lambda, some IUP lambda conjugate. Okay. So this means that each of these components lies in L lambda. What does it mean to lie in L lambda? That means that you're centralized by lambda, right? L lambda is the centralizer of the image. Therefore, lambda fixes inverse, and this is just the people. And now by the corollary that we had a moment ago, H prime is equal to U H by the corollary. So that completes the proof of one direction. That shows that if H is G completely reducible, then the orbit is closed. And the other direction, the proof is very similar. You just kind of take this argument and run it backwards, but it's actually a little bit easier. The hard thing that's buried in here is going from G conjugacy to RUP lambda conjugacy, which was taken care of by that earlier theorem that we proved. Maybe I should mention that the original proof of this result in my paper with Bate and Röhler, it's done in a different way without using this theorem 3.12. This theorem 3.12 came along later. So let's have our 5-minute break now. So I think I'll just point at the screen now. Suppose the orbit is closed. We want to show that H is G completely reducible. So take a parabolic subgroup P that contains RH. Well, by our characterization of parabolic subgroups, we know that P is equal to P lambda for some lambda. So if H is contained in P lambda, that means that each of these components, H little hi, is contained in P lambda. So that means that the limit for each of these components exists. And then when you stick the components together into the tuple, that tells you that the limit of the tuple also exists. So this limit of the tuple here exists. Let's call that limit H prime. We're assuming that the orbit is closed, so H prime belongs to the orbit. Actually, this is the direction where you have this non-trivial step where you go from G conjugacy to P lambda conjugacy. So H prime belongs to G dot H, and then by the theorem that we proved at the end of the last section, that tells us that actually H prime is RUP lambda conjugate to H. And so if you hit both sides with this U inverse, then you get H is equal to U inverse of H prime. But H prime is in L lambda Vm, because H prime is what you get by taking the limit of this H, the lambda, and with all of the components, they're all being pushed into L lambda when you take the limit. So H prime is in L lambda to the M. So U inverse dot H prime is in U inverse L lambda U to the M. But that's saying that all of the components of H HI lies in U L lambda U inverse. So that's saying that H is contained in U inverse L lambda U. But this is a Levy subgroup of P lambda.
the Levy subgroups of P lambda are all RU P lambda conjugate. And this shows that H is G completely reducible. We put H inside a parabolic, and we showed that actually it's inside some Levy. Okay. So now a remark here which I want to make, because this relates back to something that we were talking about before with GLN. Remember we did this calculation even in the first lecture, I think, for GLN, and we had these block upper triangular subgroups and block diagonal subgroups. And then a bit later on in the second lecture, when I talked about GLN K complete reducibility, I said it's equivalent to being completely reducible to representation. But I pointed out there was a subtlety which amounts to showing if H is contained in a parabolic subgroup P, and H is G conjugate to a subgroup of some fixed Levy subgroup L, then H is RUP conjugate to a subgroup of L. Okay. But that follows from this argument up here, that if you convert the corresponding statement for tuples into a statement for subgroups, this is precisely what this is giving you. Okay. So now, if you're feeling lazy, then the question in exercise 1, which is showing you to prove this, you could just appeal to this remark, although it's more instructive, I think, to try to write down explicitly a conjugating matrix that lies in RUP. Okay, a little bit of fine print down the bottom here. How do we know which subgroups of G are topologically finitely generated and which are not? In characteristic 0, every subgroup is topologically finitely generated. No problem at all. In positive characteristic, it actually depends on the field. This is something that's a little bit strange if you're used to working with algebraic groups. Generally you say, let's fix an algebraically closed field of characteristic whatever, and then the results that you get, it doesn't matter which field you choose. But here, actually, the choice of field changes whether a subgroup is topologically finitely generated or not. So there's a slightly model theoretic flavour, perhaps, to what's going on. I may have something more to say about that in the 6th lecture. So if K is the algebraic closure of a finite field, then any topologically finitely generated subgroup is finite. So why is that? Well, you may as well assume that your group is a general linear group, because you can certainly embed your group in a general linear group. So if you were looking at the general linear group over K, where K is the algebraic closure of the finite field Fp, the algebraic closure of Fp is the ascending union of finite fields Fq, where Q runs over higher and higher and higher powers of P. So any element of K belongs to Fq for some Q. So if you take finitely many matrices in GLN K, and you look at all the components will all belong to Fq. The matrix entries will all belong to Fq for some sufficiently large Q. So that will say that each of these guys will be living inside GLN Fq, but GLN Fq is finite, because Fq is finite. So the subgroup that they generate is finite. But on the other hand, if K is not the algebraic closure of Fp, then one can show that any reductive subgroup of G is topologically finitely generated. That's, there's a reference there, I won't say anything more about that. But even then you still have trouble with unipotent subgroups, because if you take a finitely generated unipotent subgroup, that's finite as well. Just because in positive characteristic, unipotent groups are always nilpotent, and in positive characteristic, they have exponent p to the power of something. Combine those states, you see that any finitely generated subgroup of a unipotent group is finite. We don't have to worry about that too much for when we're talking about G complete reducibility, because if a subgroup is going to be G completely reducible, it has to be reductive, right? So this is saying as long as the field is large enough, and you only care about reductive subgroups, you're fine. So there are various ways around this problem. I can think of at least 3. One is to do an extension of algebraically closed fields. This is saying that you have a problem if your field is too small. You can make the field larger, and then you can prove that G-complete reducibility is well behaved under extension of fields. That's one solution. Second solution is to use this observation here, which is going to be an exercise. For any h, you can find a topologically finitely generated h prime, which is contained in exactly the same parabolic subgroups and Levy subgroups as h. That means that as far as G-complete reducibility goes, h and h prime can behave exactly the same way. Yeah? You can even, I didn't write this down, but sometimes we care about things like the centralizer of our h. By making h prime large enough, you can ensure that it has the same centralizer as h inside G. So that's another solution. A third solution is when we're looking at these limits and co-characters. There's something called uniform instability that I might mention briefly later, where rather than looking at what a co-character does to one point, you look at what co-characters do to whole subsets. And that's yet another way of getting around this problem. But our solution for this problem, for the purpose of these lectures, will be just to ignore it. So we'll just pretend that every subgroup is topologically finitely generated, just to keep life simple. And you just have to believe me when I say that this is not a problem. So the point of doing this was that I promised you that we should be able to derive some consequences for G-complete reducibility from this geometric criterion. So here's the first. Suppose we have a G-complete reducible subgroup H, and let's assume it's topologically finitely generated. Then its centralizer is reductive. And that follows from some geometric invariant theory. By the theorem we just proved, the orbit is closed, and by a result from geometric invariant theory, a result of Richardson, if you have a closed orbit, then the stabilizer group is reductive. So stabilizer, this is our notation for stabilizer G sub H, is reductive. But it's clear that the stabilizer of your tuple H is precisely the centralizer of H, right? What's the stabilizer of the tuple H? It's all the little g's that commute with all of the elements h1 up to hm. But if something commutes with h1 up to hm, it will also commute with the group of big H that's generated by h1 up to hm, and vice versa. And then if you push this argument a little bit further, you can show that the normalizer of a G-completely reducible subgroup is also reductive. Later on we're going to show a stronger result. We're going to show that centralizers and normalizers of G-completely reducible subgroups are actually G-completely reducible. That's stronger because remember a G-completely reducible subgroup is automatically reductive. In order to do that, we're going to need some stronger results from geometric invariant theory, and that's what I'm going to be talking about in the next section. So the next section will be some more geometric invariant theory, followed by some more consequences for G-complete reducibility. So I've got a couple more results that I want to state. First, we need to define a couple of things. We need the notion of a separable subgroup and a reductive pair. So if H is a subgroup of G, well, G acts on its own Lie algebra by the adjoint action. So in particular, H acts on the Lie algebra. And then the notation, this is like a Gothic lowercase version of capital C, capital G, capital H. This is the fixed points of H. So this will be some subalgebra of of the Lie algebra G. Subalgebra. Now, if you look at the Lie algebra of the centralizer, this is always contained in here. Yeah? It's always that. H acts trivially on its centralizer, by definition of the centralizer. And when I say acts, I mean by conjugation. And so therefore it has to act trivially on the Lie algebra. The Lie algebra is the tangent space of the identity. If H is not doing anything to this variety at all, then it's also not doing anything to any of the tangent spaces. H fixes the Lie algebra. And when I say fixes, I mean fixes pointwise. Centralizes everything there. Therefore, the Lie algebra of the centralizer is contained in this set, in this subalgebra of fixed points. And we say that the subgroup is separable if this inclusion is equality. Okay, it's actually possible for this to be strictly bigger than this. So I should give an example for one explicitly in notes. H is separable. We have equality. Now, the word separable is coming up a lot in these lectures. The kind of the root of all this is the notion of a separable field extension, right, which you may or may not be familiar with. And then this allows us to talk about when a dominant morphism of irreducible varieties is separable, because then you get a inclusion of function fields going the other way, so you get an extension of fields, and you can talk about whether that's separable or not. There'll be a little bit of stuff about this appearing in the exercises. The second set of exercises, by the way, I've written. I just need to tidy up a bit, so they should be ready for you by lunchtime. Be able to enjoy them with your lunch. And now this notion of separability, what does that have to do with what I just said? So if H is a subgroup generated by some tuple, it's topologically finitely generated, then H is separable if and only if the orbit map from G to the orbit is separable. So where does this come from? This comes from the derivative criterion for separability. So this is a standard result from algebraic geometry that I was actually going to set as an exercise in the first exercise sheet, and then I decided that it was too difficult. I didn't actually know how to do it. So it's just one of these exercises that, you know, you work in a subject. You maybe work in a subject for a long time, but maybe there are still these very basic and fundamental things that you've never actually gone through the proof of. I mean, this is one of them. Anyway, it looked a bit too complicated. So this says that a map like this is separable if and only if the derivative of the map is surjective at almost all points. And because this is an orbit and everything's homogeneous, the group G is acting transitively on everything, that's equivalent to saying that the derivative at the identity is surjective. What's tangent space? This is my notation for tangent space. But what is this tangent space? This is the Lie algebra. And it turns out that the kernel of the derivative is precisely this subspace here. Let's calculate. And now just counting out the dimensions of everything, you know what the dimension of this is. It's the dimension of G minus the dimension of big CG of H.
and then counting up dimensions, you see that in order for this to be surjective, you have to have, this should have the same dimension as big CG of H, and that's equivalent to saying reducibility. And then there's this further characterization, which is saying that the scheme theoretic centralizer, for those of you who have come across group schemes of H and G, is smooth. This scheme theoretic beast is actually a variety. Don't worry about that, we don't really need it. And then on top of that is what I just said, stuff about the orbit map. So let's do an example. Let's take our old friend SL2 and characteristic 2, source of bad behavior. Separability is a low characteristic behavior. So Sebastian Herpel, who is now left mathematics, unfortunately, it's very good, proved that if you fix G, then if the characteristic of the field is large enough, then every subgroup is separable. And we're going to see in a minute that the hypothesis of separability comes into a lot of these results concerning G-complete reducibility. If subgroups are separable, nice things happen. If subgroups are not separable, then bad things can happen. You can get these pathologies in low characteristic. We're talking about that in a minute. So example, G equals SL2. Let's take a stupid example. Let's just take H be equal to the whole G. So what's the centralizer of H? Oh yeah, equals 2. Well, let's do arbitrary. CG of H is the centre of G, which is just plus or minus the identity. So this has 2 points or 1, depending on whether you're in characteristic 2 or not. But anyway, the dimension is 0. It's a finite set. So the Lie algebra of CG of H is just 0. What about the Lie algebra centralizer of H? This is the Lie algebra centralizer of G. So you have G acting on the Lie algebra by the adjoint action, and you're asking, what are the fixed points? If you're not in characteristic 2, remember that G is acting irreducibly, and so in particular you don't see any fixed points. This is 0 if the characteristic is not 2. On the other hand, if the characteristic is 2, then we have this one-dimensional stable subspace, not just stable but fixed, which is the centre of the Lie algebra, and it's actually fixed under the adjoint action, because the adjoint action is conjugation, and this one-dimensional subspace is just scalar multiples of the identity. So it's scalar multiples of the identity. So this has dimension 0, and this has dimension 1. So H is separable if P is not 2, and non-separable if P equals 2. Okay, it's a fairly stupid example, but it does illustrate the definition. I mean, it's more interesting to look at proper subgroups that are separable, other than for stupid reasons like this, which is that the Lie algebra itself has centre of dimension greater than the centre of the group. And then the other notion is reductive pair. You say that G comma M is a reductive pair. So here, well, G is a connected reductive group as always. M is a connected reductive subgroup, although in general we would allow M to be non-connected just as we would allow G to be non-connected. So what does this mean? This means that the M submodule Lie algebra sitting inside the Lie algebra of G. So big M acts on the Lie algebra of G via the adjoint module. The Lie algebra of M is sitting inside the Lie algebra of G. Whenever you have an inclusion of groups, you have an inclusion of Lie algebras. This is probably something I should have written down when I was talking about Lie algebras at the beginning. I think I said it, but I didn't write it down. So this is a subset of here, and it's a submodule for the big M action. Big M stabilizes its own state, its own Lie algebra. M stable. So this is always true in characteristic 0, because in characteristic 0, linearly reductive groups are linearly reductive. So this is saying that M acts completely reducibly on the Lie algebra of G, so there will be a complement. In positive characteristic, this can fail. I think a good example just off the top of my head. But again, this is a low characteristic phenomenon. Well, as we will see in a minute in some examples where you do have reductive pairs. Okay. Next result. So suppose M is a connected reductive subgroup of G. GM is a reductive pair. H is a subgroup of M. Suppose that H is G completely reducible and separable in G. We can talk about whether H is separable in M or separable in G. We want it to be separable in G. Then H is M completely reducible. So remember this very general problem that we were talking about in the second lecture. H sitting inside an M, sitting inside G. H, M completely reducible. Is that equivalent to saying that H is G completely reducible? And as we saw, the answer is no in general. We had some counterexamples, but many of the counterexamples seem to be somehow tied up with bad characteristic. So one of the interesting questions in this subject is trying to figure out what it is that causes the bad examples, trying to isolate that property, and then you're able to say, well, as long as this bad property doesn't hold, then everything's quite nice and well behaved. And the closest we've got to doing this is separability. Lack of separability seems to be what causes most of the pathological or interesting, depending on the point of view, behaviour. So I'm going to sketch a proof of this because I think the argument is really nice. It's probably you'll find it fairly heavy going if you're not very familiar with algebraic geometry, and in particular the notion of a tangent space. I'll try my best to explain what's going on. So let's assume that our H is topologically finitely generated, and then so we assume that H is G completely reducible. Then this tells us that the orbit of this tuple is closed. Closed in what? It's a closed subset of GP. Now we want to prove that big H is M completely reducible, so we want to know that the M orbit of this tuple is closed. Yes? And then again by theorem 4.1, that will tell us that H is M completely reducible. So we want to show So now let's look at the big orbit. Let's look at the intersection of the big orbit with big M to the little m. So this is contained in, the little orbit is contained in the big orbit. You see it. Big M. Little m. Maybe I should have chosen a different letter. And so the way we're going to get at this is by studying how this is sitting inside here. Okay. Notice that this is a union of M conjugacy classes. Okay. It's clear that this subset on the right hand side is M stable, because after all the G orbit is M stable because it's G stable, and M to the M is M stable. Okay. And what we're going to prove, I haven't written this. I haven't written this down, but I think this is a useful point of view. That these are equal locally. So in an open neighborhood of this generator. So not really sure that I can draw a picture of this. Let's try. So here's a small set. Think of this as this guy. And let's draw a big set, a green guy, which contains all of the black guy and some other stuff. Yep. So saying that they're equal locally, here's my point. I mean in some open subset of this point. The only green stuff that you see is the black stuff. You don't see any of this other green stuff. And it will follow from this that the black stuff and the green stuff have the same topology locally, and therefore we know that the green stuff is closed. That's the stuff on the right hand side. This is closed because this is closed and this is closed, and therefore it will follow that the black stuff that we're interested in is closed. Now, in order to show that the green stuff and the black stuff are equal locally, we can do that by showing that they have the same tangent space. Right? If you have two manifolds, a small one contained in a big one, and you take a point in the small one, and the tangent space of the small one is actually equal to the tangent space of the big one at that point, that's saying that those two manifolds have the same dimension at that point, and that's saying that they're locally equal. It's a similar sort of argument that's going on here in the algebraic geometry. You have to be a little bit more careful because in algebraic geometry you can have singularities, and at a singularity the dimension of the tangent space can jump. There are some little details here that I'm suppressing. So I think we should be able to get the proof of this, and then we'll be able to stop. Then it'll be time to stop. We've got through most of section 4. So the three main results that I wanted to prove in section 4, and this is the third one. So we're going to look at the tangent spaces. So if we take some point G, what can we say about the tangent space? Well, the idea is that we can use inverse right multiplication. So what do I mean by that? Say,
mean by inverse right multiplication by this fixed g. This is some morphism from g to g, and then the derivative of this at the point little g, we take the tangent space of big G at little g to the tangent space at phi g. But phi of g is just the identity. And this is the Lie. Okay? So we can identify the tangent space at any point in the group with the Lie algebra. Why do we do right multiplication rather than left multiplication? Just because that makes things work out nicely. Those of you who've come across Lie groups before, maybe you've heard of the Lie algebra is described as the left invariant vector fields, and it's the same kind of idea. You can kind of translate the tangent space of the identity around to different points in the group. And so this tells us that we can think of the tangent space at some point in GM, at this point here. We can think of this as the product of m copies of the Lie algebra. So we equal, we can identify. So then you can ask yourself, well, what's the tangent space of this G orbit? What does the tangent space of the orbit look like? And separability tells you that the orbit map is surjective at the level of tangent spaces, and so that says that you can compute this tangent space as being the image under the differential of the orbit map of the Lie algebra of G. And that gives you this formula, this complicated looking formula. The tangent space of the G orbit you can think of as I realise this looks kind of complicated, but at least I hope you'll agree with me that this is sitting inside G. So X is some element of the Lie algebra of G. You're hitting it with these HIs under the adjoint action. So X minus H1 of X. And so on. And we get the same thing for M. It's exactly the same. This time you're just running through the Lie algebra of M. Now remember, we are interested in the G orbit, the big orbit, intersect M to the M. So we want to know, in this tangent space here, which is the tangent space of the big orbit, which of these tangent vectors actually lie in the Lie algebra of M? Because these are the ones that we care about if we want to look at the tangent space of this smaller set. Whatever these tangent vectors are, then they have to lie in the Lie algebra of the components have to lie in the Lie algebra of M. So you ask yourself, under what conditions, for what x's, will it be the case that if I do this, and remembering that these HIs belong to M, under what conditions on X in the big Lie algebra will it be the case that all of these components belong to the smaller Lie algebra? And the reductive pair condition tells you that that will happen if and only if you're in here. If and only if you can choose an X that belongs to the smaller Lie algebra. Okay? So there's a calculation that's involved there, and this is the upshot. This kind of complicated thing, this tangent space that you don't know very much about, actually just coincides with the tangent space of this smaller orbit. and this tells us that the black stuff and the green stuff that I drew before are locally the same, and we can deduce from this that the orbit is closed. And that's the end of the proof. Alright, we still have a little bit of time left, so I'll press on. This comment is reasonably gentle. So another consequence of this is that actually this is a finite union of M conjugacy classes. Okay? So you're taking a tuple in M, you're taking the G orbit of that, you're intersecting that with M to the M, and you're only seeing finitely many M conjugacy classes. Remember I said before that certainly it's some number of M conjugacy classes. This argument shows that it's finite. Again, that this just drops out from saying that these tangent spaces are the same, it's saying that these things have the same dimension. This result falls out. So here's a counterexample, example 2.11. Absolutely no reason why you should remember what example 2.11 was, but this was an example of H inside an M inside G, and G was of type G2, and M was of type A1 cross A1, where these were short roots, and H was isomorphic to S3, where H is GCR, but not MCR. Now it turns out here that G comma M is a reductive pair. Essentially because, if you know what this means, the short root subgroup, it's regular, it contains a maximal torus of the group. The complementary subspace of the Lie algebra is just going to be, so this involves certain roots of G, the complementary subspace is just going to be spanned by all of the other roots. And this works because we see this subspace in arbitrary characteristic. If you do this with B2, in B2 you have a long root A1, which you always see, and you get a reductive pair. In B2 and characteristic 2, you get a short root A1, and you will only see that in characteristic 2, and then I think that guy is not a reductive pair. Don't worry if you didn't understand anything. Instead, it's just experts on algebraic groups in the audience. So this is a reductive pair. H is GCR, but not MCR. Okay? Why does this not violate the theorem? Well, of course it doesn't violate the theorem, it's the theorem. The reason is that the hypotheses of the theorem are not satisfied. One of the hypotheses of the theorem is satisfied, this one. So the other one must be false. So that's saying that H cannot be separable in G. Because if it was, then the proposition wasn't it, that we just proved would apply, and that would say that since H is GCR, H would have to be MCR. Okay? So the problem here really is due to a lack of suitability. And then if you modify the construction slightly, the construction of this H, you also get, you can find pair, property there. If you look at the G orbit of this pair and intersect that with M squared, that this is an infinite union of M conjugacy classes. Okay? And again, the argument of the proposition that we just went through tells us that this can't happen under the hypotheses of the proposition. One of the hypotheses of the proposition is true, it's this one here. So the one that must fail must be susceptibility. So if you look at the subgroup generated by this, topologically generated by this pair,
this is not separable. Okay, that's a good place to stop.
Ready. But now we have a break before 10 to